Hi everybody. So we've been talking about acids, we've been talking about bases, and now we're going to see what happens when we put them together. So we're going to start off with a really simple reaction between an acid and a base. And I have a really good story to tell you about this one in a few minutes. So our classic example of an acid-base reaction is this one. Hydrochloric acid plus sodium hydroxide yielding sodium chloride, water, and energy. So our acid in this case is our hydrochloric acid. That's pretty obvious. Our base in this case would be our sodium hydroxide. And then we get our sodium chloride. And sodium chloride is a salt. It is an ionic substance. And then we also get water and energy. And that release of energy makes our reaction exothermic. This is a classic neutralization reaction. Okay. Now, let's look at the ingredients here. We've got hydrochloric acid, okay, usually a very strong acid. We've got sodium hydroxide, strong base, and what do we get out of it? We get sodium chloride and water. Back when I was in college, the first day of class when my professor was teaching us about neutralization reactions, remember his name was Dr. Babb, and he's since passed away a few years ago, but he came into the classroom, and it was one of those old-fashioned lecture halls, and he had two Erlenmeyer flasks in his hands, and he started talking about acids and bases, and did a pH test in each one and showed us that the hydrochloric acid was really strong. It was like a pH of 1, and the sodium hydroxide was really strong. It was like a pH of 14, and he kept going through his lecture, and then about halfway through, he poured the two flasks together in a third beaker, and then he picked it up and he drank it. And all of us were pretty much certain that we were going to be needing to run out into the hallway and call 911. But no, he took a big sip and he was fine. Well, how did he survive that? He took a strong acid and a strong base, mixed them together, and then he drank it. Well, the reason why he was fine is that he was a very precise chemist. And the strength of that acid and that base were so precisely balanced that he got a perfectly neutral sodium chloride solution at the end that you wouldn't want to chug. Salt water, drinking salt water is not great. It can make you throw up. But taking a little sip of it was perfectly safe. Now, let me tell you, I don't think I would have the faith to do that. I wouldn't trust my lab assistant, nor would I necessarily even trust myself that much. So let's go into our acid-base reactions a little bit further with neutralizations. So a classic neutralization always involves an acid and a base, and we're talking about Arrhenius acids and bases here, and they always produce a salt and water. Now this only occurs once again when using Arrhenius acids and bases. We're not talking about alternative theory or Bronsted-Lowry here. Now why is this? Well, in order to create the water that's produced, we have to have hydrogen being supplied by the acid, hydrogen ions, and hydroxide ions being supplied by the base. And there also have to be metal and non-metal ions available in the solution to create our salt. And the hydrogen and hydroxide ions, as I said, have to be able to create your water. So once again, going back to our classic example of a neutralization reaction, here we have an example which is a strong acid versus a strong base. Here we have a weak acid versus a strong base. What do you think would happen when we mix a weak acid and a strong base? Do we get a neutral solution? Well, in this case we wouldn't. Our solution would remain slightly basic, but we would get some sodium acetate in this case, and water. However, some sodium hydroxide might still remain in solution. So this would be a situation where we would end up with something slightly basic because our base was stronger than our acid. So salts can be neutral, acidic, or basic. All right. So neutralization can only occur, and we're talking about a true neutralization, can only occur when equal amounts or concentrations of hydrogen ions from the acid and hydroxide ions from the base are mixed. So our hydrogen ion concentration must equal our hydroxide ion concentration. If we have more hydrogen than hydroxide, we're going to remain acidic. And if we have more hydroxide than hydrogen, we would remain basic. Now, I want you to go to table I on your reference table and take a look. The very last equation on table I is a simplified neutralization reaction. And I'd like for you to write that in your notes. What you should have had was hydrogen plus hydroxide yields water plus energy. Now, table I tells us that we're definitely releasing energy because the delta H that's given is a negative delta H, and that's just a reminder for you. Remember, whenever you have a negative delta H, you have an exothermic reaction, which means energy is being released. So, I'm going to give you some examples. We could have phosphoric acid and ammonium hydroxide. Well, what would our salt be here? Well, our salt is going to come from whatever went into the acid and the base that isn't hydrogen and hydroxide. So we're going to look at this phosphoric and, the ammonium. So we would get ammonium phosphate. Now, what would go together to make magnesium nitrate? Well, this magnesium is a metal, which means it had to come from the base. Now, when we have a base, it's a metal plus hydroxide. So that means that our base had to have been magnesium hydroxide. And here, our nitrate had to come from our acid. It would be this nitrate plus the appropriate number of hydrogens, and that would give us nitric acid and magnesium hydroxide. Water will also always be one of our products. I want you to recognize that if you're given the acid and the base, you should always be able to predict your salt, that is your product. And if you're just given your salt, likewise, you should be able to determine what your acid and your base. All right, let's do some examples. Look at example 16. Which word equation here would best represent a neutralization reaction? Well, here your best choice is choice 1. Base plus acid yields salt plus water. Let's look at another example. Now, this one's significantly long, and I'm going to give you a few minutes to work through each part. Let's look at the reading passage together. Soil pH can affect the development of plants. For example, a hydrangea plant produces blue flowers when grown in acidic soil, but pink flowers when grown in basic soil. Evergreen plants can show a yellowing of foliage called chlorosis when grown in soil that is too basic. I'm just underlining some of the key terms as we're going through. Acidic soil can be neutralized by treating it with calcium hydroxide, commonly known as slaked lime. Slaked lime is slightly soluble in water. So let's look at question A. It says compare the hydrogen ion concentration to the hydroxide ion concentration in soil when a hydrangea plant produces pink flowers. I'm going to give you a chance to try to answer this on your own. Take a moment, go back into the reading, and see what you can find. Well, if we're looking at this, the thing to remember is that hydrogen ions come from acids and hydroxide ions come from bases. And we're making pink flowers. In our reading passage, it says that we get pink flowers in basic soil. So that means we have to be a base. So that means our hydroxide ion concentration would be greater than our hydrogen ion concentration because it's a base. All right, let's look at part B. An evergreen plant has yellowing foliage. The soil surrounding the plant is tested with methyl orange and bromothymol blue. Both indicators turn yellow in the soil tests. State in terms of pH value why the yellowing of the plant is not due to chlorosis. So you're going to need table M to solve this, and I'm going to give you just a moment to look through the reading passage and see if you can come up with an answer. Well, we're testing with methyl orange and bromothymol blue. Both of these indicators turn yellow. Well, we know, according to table M, that bromothymol blue, well, let's start with methyl orange, that methyl orange is yellow above 4.4. We know that bromothymol blue is yellow below 6.0. So that means we are between 4.4 and 6.0, which means that we are definitely in the acidic range. Now, the reading passage said that we have yellowing foliage called chlorosis that only happens when the soil is too basic. So that means the yellowing of this plant can't be due to chlorosis because its pH is in the acidic range. Let's look at part C. Write an equation using symbols or words for the neutralization of the ions in the acidic soil. So we're looking at hydrogen ions plus hydroxide ions producing HOH or water. Well, that was really messy. That is your classic neutralization equation. And once again, you can find that at the bottom of table I. All right, let's look at two more questions. Given this balanced equation representing a reaction where you have sulfuric acid reacting with potassium hydroxide to form potassium sulfate and water, what type of reaction is represented by this equation? That would be a neutralization. We have an acid and a base producing a salt and water. Let's try example 19. Once again, you can find these examples on page 26. Example 19. As the pH of a solution is changed from 3 to 6, the concentration of hydronium ions does what? Try to answer this one on your own, and then I'll give you some clues. So hydronium ions, just like hydrogen ions, are produced from acids. Okay, so we're talking about when we go from 3 to 6, what happens to the concentration of the hydronium ions? So as we go from 3 to 6, are we becoming more acidic or are we becoming more basic? We're becoming more basic, which means we're becoming less acidic. So our hydrogen ion concentration will be decreasing. But how much will it be decreasing? We know one of those is our choice. Well, each step on the pH scale is a factor of 10. So we're moving from 3 to 6. 1, 2, 3 steps. So that would be 10 times 10 times 10. So the correct answer would be that it decreases by a factor of 1,000. Choice C is the most common wrong answer because people see 6 and 3, they subtract 3 from 6 and they get 3 and they think that's the answer. Remember, each step on the pH scale is a factor of 10. All right, so from here you're going to go on and practice some neutralization questions. And in our next video, we'll be talking about the reactions of acids with metals.